Okay, so in this video I'm going to go through a problem I came across when I was preparing for my own Cambridge admissions interview called the weird resistor problem. It was one of the more difficult problems I encountered, and I think it's a good problem to provide an example of how to tackle a seemingly impossible or daunting problem by breaking it up into smaller components that you can then deal with and then reconstruct into a final solution, and to just make sure you're aware that you're not going to be testing on anything that you haven't already covered at uni. So just before we get into it, you need to be pretty good with your trig and your calculus getting into this, because this question actually requires you to form your own integral. And you need a bit of circuits knowledge, so you need to know how power is dissipated in resistors in series, and you need to know about resistivity. The relevance for this is very, like I say, towards Cambridge and Oxford admissions interviews, and also STEP papers have this sort of question occasionally. So here is the question. A weird-looking resistor, which is made up of a solid lump, is pi/4 meters long, and has the same shape as a sec-x curve rotated 360 degrees about the x-axis. A side and 3D view of the resistor are shown in the diagram. Given that a constant current I flows through the resistor, thanks to two electrodes placed at each end on the circular surfaces, calculate the power dissipated using the information provided above. So using what's in this box, you have to find the power dissipated by a resistor that looks like that. Now that is, of course, a big question mark. When I first saw this problem, I didn't know how to tackle it. I panicked a bit, and it is quite difficult, but you have to just keep your cool and think. Get your information together. So as highlighted there, we're given a current, we're given a resistivity, so you should be thinking along the lines of power dissipation there. I have a current, and I might be able to get a resistance, so you've got your I squared R. But two key pieces of information on this page are the R1 and the R2 values. So we're going to call the start of this shape x equals 0, and we're going to call this point x equals pi/4. Now we're told that it looks like a sec curve, the shape, as you can see here. It says it's a sec-x curve. But sec of 0 is 1, and sec of pi/4 is root 2. So there's clearly a constant factor there, which is just 0.001. So the shape of the curve is r of x equals k sec x, where k is 0.001. And that's the key piece of information that you can sort of derive from those two radius values. We now know how the radius changes with x, so we know what the sort of shape of that curve is that this resistor takes. And then we can use this later on to find what we're going to need to do. So that's our information collection. We've looked at the information and we've gone, what can I get out of these numbers that I've been given and the information in the question? Next, you need to look at, what do I know? What do I actually know that will help me solve this problem? Well, you know that you need to find the power dissipated in the resistor, and you know that P equals I squared R. That's a bad 2. And we're given a resistivity. So we know what I is, but we don't know what R is. But we are given a resistivity here. So we can find a resistance, or we can see if we can find a resistance by using the resistivity formula, which is R equals rho L over A. So where this is L, the length of the resistor, and the area is this sort of cross-sectional area. But there's a bit of a problem here. So we know that the length of the resistor is pi/4, but what's the area? The area is sort of constantly changing. As we go through, it's going to get bigger and bigger as we move, as the current moves through this resistor. So we don't have a constant area. What we actually need to look at is the sort of cumulative effect of that constantly changing area on the resistance of this geometry. Which, whenever you think about cumulative effects, you should think along the lines of integration and breaking something down to small parts and then adding them back up. That's a very key thing for sort of Oxbridge interviews. If something's constantly changing and you need to look at a sort of cumulative effect of that constant change, you need to think about breaking it down and then summing it back up, or integrating it back up. So we're going to break it down. And what we're going to do is we're going to break it down into lots of small circular discs that look a bit like this. This is a bit exaggerated, obviously. And the width of these discs is dx. They have a radius r, and they're so thin, dx is such a small number that we're actually just going to ignore the sort of change in radius of these discs as we go through them. We're just going to say that they're perfectly circular discs. And then that's going to allow us to find the area. The cross-sectional area of these discs, A, is pi times r of x squared. Remember that the radius changes with x. And then we can find the resistance of one of these small discs. So the small resistance, dr, of one of these discs is going to be the resistivity, which is constant in the material, times the length of it, which is dx here. So that's our L, over the area of the disc, which is, or the cross-sectional area of the disc, which is pi r of x squared. So that's a small area, that's the resistance of pretty much a small slice of this shape. How do we then use this to find the total resistance? Well, what we do is we sum these up across the whole length of the shape, and when we sum up very small elements, is what we call them, that's actually called an integral. That's what integration is. It's not very well taught at school in my experience, but we'll find that we can get the total resistance by actually integrating dr, or summing up all these small resistances. And we know what dr is. That's going to be the integral between 0 and pi over 4, it's a bad pi, of rho over pi times 1 over r of x squared dx, where I've just swapped out dr for this expression here. And I've just added in the bounds because we know that we're summing from x equals 0 to x equals pi over 4. If we substitute in our expression, which is r of x equals k sec x, for r of x, you should note that r of x is sec x, so 1 over r of x is cos x, and 1 over r of x squared is then going to be cos squared x, or 1 over k squared cos squared x. So we're going to get which equals rho over pi k squared, is equal between 0 and pi over 4 of cos squared x dx. I'm not going to do this integral. You should be able to integrate cos squared. I think it comes out as a half x plus a quarter sine 2x. But the value of this whole expression ends up coming out as about 0.086 ohms. So that's your resistance of this shape here. So we can now put it all together, take that 0.086, say that P equals I squared R, which equals 3.41 squared times 0.086, and as it so happens they were pretty clever with the question and the numbers, and that comes out as 1.00 watts. So it dissipates 1 watt of power, and that's that. That's your solution. Obviously, things you should be in the interview, you need to be careful to check. Make sure your equation for the curve is right, that you've used these values properly. Have I used all the information I'm given? That tends to be a good hint. They'll never give you a question with sort of redundant pieces of information or useless pieces of information. So yeah, I've used R1, R2, I've used rho, and I've used I. I've taken into account the fact that it's a 3D shape, not just 2D shape, when I was calculating the areas. So it's looking pretty good. So I can be confident that the answer is 1.00 watts, and that is what the answer is. Some questions that I get asked when I'm told, like when I get people who are applying to Oxford or Cambridge and ask me about things, I normally point to this question and they're like, oh, too hard, I can't possibly do that in an interview. And yeah, without practice you can't. You need to prepare, and the best way to get to be able to do these is to do questions similar to them. And once you've done a few, you start to get the hang of it, and you start to see where you need to get an integral, why you need to integrate, why I broke it down into these small shapes. And it eventually comes quite naturally, and it's something that will really impress interviewers. And in your interview, you won't also be alone. The interviewer will guide you through these problems. You're not going to be, if you get stuck, which everyone gets stuck in Oxbridge interviews, then you'll be guided through, and the interviewer might suggest breaking it down into small shapes and then integrating or something like that. Where did this question come from? There's a great resource called iwanttostudyengineering.org, and it's really one of the best resources for preparing for Oxbridge interviews, especially for engineering, which is what I applied for. And there's tons of questions on it, I think about 100 or so. And this is one of the harder questions, for sure, and definitely one of the longer questions. But if you work your way through that question list, then you're going to be in a really good position if or when it comes down to having an interview.